Okay, and we're back. So we are continuing with the second example problem of the intermediate value theorem. So this one says, the position of a particle is given by a twice differentiable function, p of t, if p prime of 6 equals 20 and p prime of 10 equals negative 5. Show that the particle turns around at least once on the interval 6, 10. Okay. So, we're not given an actual equation, for P, and that's fine. We're given enough information here. So, I want to use the intermediate value theorem. So there are a couple things I, want to figure out here. So, first, the function, the particle, turning around, that means that P prime, so we are looking for some time, we'll call it k. So we are trying to prove that there is a value of k in this time interval in between 6 and 10 seconds where p prime is equal to 0 and p prime changes from positive to negative. Okay, so first we want to notice that p prime of 6 is 20 and p prime of 10 is negative 5. So 0 is between negative 5 and 20. All right, so I don't know what p prime looks like, but in between 6 and 10. I know that at 6, p prime is 20. And I know that at 10, p prime is negative 5. So 0 is, in fact, in between negative 5 and 20. So we know that's true. That's one of the conditions for the IVT, is that the y value we're looking for be in between the y value at the beginning of the interval and the y value at the end, so check. The next thing we need to verify is that p prime is continuous. So here's an example of where we are given some key information sort of in code here. We are told that p, the position function, is twice differentiable. So because of that, that means that both p and its derivative are differentiable. So p prime is differentiable because it was given in problem that p is twice differentiable. So if a function is differentiable, so p prime of t must be continuous, because if a function is differentiable, it has to be continuous. Because differentiability implies continuity. Therefore, the intermediate value theorem says that p prime must pass through 0 somewhere between t equals 6 and t equals 10. Which means that it has to have a turning point. So p prime passes through 0 in between 6 and 10. That means the particle has the position function has a turning point somewhere between 6 and 10. Okay. So not a lot of computation in these kind of problems. There's a decent amount of writing and explaining. Okay, we're going to move on to a different VT. This one is the extreme value theorem. This one says something that's like even more obvious. Okay, if a function f of x is continuous on the closed interval a comma b, then f of x has both a minimum and a maximum on a comma b. Yeah, that's pretty commonsensical. We've been finding turning points, which are minimum and maxima, for a while now. All this theorem is saying is that if you are looking at a closed interval, so that means the two endpoints are included, then the function has both a minimum and a maximum on that interval. The new thing here is that the minimum and maximum on that interval might be at the endpoints. It may not be the turning points. So to draw a graph of this, so let's say I am looking at a function on this interval, and it looks something like this. So if I take the first derivative, set it equal to 0, and solve, I'm going to find this turning point and this turning point. Those 2 points are, in fact, the minimum and maximum on this interval. However, if the function looks something like this, right? If I take the first derivative and set it equal to 0, I'm going to find this minimum and this maximum. This minimum is, in fact, the actual minimum of this function on this interval. However, the maximum is not this point. It is not the turning point on here. This is not the maximum. The maximum value of this function on this interval is actually here at the endpoint. So for these problems, what you're going to do is you're going to go ahead and you're going to find the turning points. You're going to find the y values of the turning points. You're going to figure out if they're min or max. And then you're also going to find the y values at either end of the interval. And you're going to see if those might replace the minimum and maximum from the turning points you found. So let's go ahead and do this problem. We're given f of x is 2/3 x cubed minus 21/2 x squared plus 40x, and the interval we're looking at is 0, 15. So let's go ahead and find the minimum and maximum. I'll let you put that in a play posit. I want you to find turning points on this interval, and I'm going to pause it and put up the solution. Okay, so here's the work to find the turning points of this function. I took the derivative f prime of x. I got 2x squared minus 21x plus 40. Set it equal to 0. I factored. I got critical values at x equals 5/2 and x equals 8. Came over here, did my first derivative test. Got these. I found that 5/2 is a maximum, because the derivative is going from positive to negative. And then that x equals 8 is a minimum, because the derivative is going from decreasing to increasing. So then to find the y values of those points, I went back and plugged in the numbers. And yes, I did use a calculator to do these. When you plug in 5/2 into the original function f of x, you get 44.79. When you plug in 8 into the original function, you get negative 10.67. So far, this is when we would be done with the problem. But now we need to find out, are these actually the minimum and maximum values on these intervals if we check the endpoints? So we need to find f of 0 and f of 15. So I'll do the endpoints in green. I'll do f of 0 for you. F of 0 is 0. When you plug in 0 for x, you get 0. So go ahead and figure out what f of 15 is. I'll let you put it in. Okay, so f of 15 is 487.5. So now when we look back on the minimum maximum that we computed using the derivative, the minimum value we got was negative 10.67. That is actually lower than both of the two endpoints, so negative 10.67 is the minimum value on this interval. When we look at the maximum value we computed, we got 44.79. Unfortunately, the function, well, unfortunately, who cares? The function has a value much larger than that at the right-hand endpoint when x equals 15. We got a value of 487.5. So the maximum value of this function on this interval is 487.5. It's not actually a turning point, but it is the maximum value on this interval. So same as usual in terms of finding turning points. It just has that extra step at the end where you need to compare your min and max to the values of the endpoint. Okay, and that's about it for the extreme value theorem. It's not very extreme. Okay. Got 5 more minutes on this video. Okay, so the last one, the mean value theorem. If a function f of x is continuous and differentiable on an interval a comma b, then there exists some x value c between a and b such that f prime of c equals f of b minus f of a over b minus a. Okay, so in common tongue, this whole shebang here should look familiar. This is the average rate of change between a and b. And this just means the derivative, so the slope of a function f. So in common language, if a function is continuous and differentiable between two x values a and b, then somewhere between a and b, the slope or instantaneous rate of change or derivative, whatever you want to call it, of f of x is equal to the a rock between those 2 points. So let's draw an example. Let's say I've got a function that looks like this. And this is a, and this point is b. Okay, so remember, a rock is the slope of the secant line that connects 2 points on a function. So the a rock is the slope of this line. And all this theorem is saying is that if a function is continuous and differentiable over this whole interval, then somewhere in between these 2 points, there is a point where the instantaneous rate change, or the derivative of the function, is the same as the average rate of change. So another way to say that is that there's a point where the slope of the tangent line is equal to the slope of this secant line. Which makes sense, you know, if a function starts really steep and it ends up really flat, and it's continuous and differentiable everywhere in between, then there must be at least one point in between here where the slope of the function passes through the average of the beginning and ending slopes. So that's what it says. Again, it has the same if conditions at the beginning. The function we're looking at has to be continuous and differentiable in order to apply this. So let's look at an example of when we might use this. These problems tend to be a little bit more recognizable because a lot of times they will say mean value theorem in them. Okay, so here's an example. We're given a function f of x. We want to see that we want to check and see that the MVT applies on this interval, and then find the equation of the line tangent to f of x at the point guaranteed by the mean value theorem. So I think, whoops, I forgot to turn off the pen. So I think this function looks something like this, if I'm not mistaken. Here's like maybe 1, and here's 4. So we want to check to make sure that the MVT, the mean value theorem, applies. In this case, meaning we need to confirm that f of x is continuous in between 1 and 4. And then we want to find the coordinates of the point where the derivative, or rate of change of f of x, is equal to the slope of this tangent line, or of this secant line. So to do this problem, you need to find the average rate of change on this interval. Then you need to take the derivative of the given function and set it equal to that. So find a rock, to take derivative and set it equal to the a rock. Solve for x. That will tell you where this point is, and then plug x into f of x. And that'll give us the point, and we'll use point slope form. Okay, I'm going to pause it, and the solution will appear. Okay, we're running out of time on this video, so you can pause this and take a look at this and go through the work. It's color-coded which step. The last part here in gold, I just figured out a point, and we knew the slope was 1, and I plugged it into point slope form to get